Hi again, it's Manu, back for another video tutorial on the second cache problem from the review. So this is on slide 58, and it's the second out of the two cache problems. So I'm going to go a bit faster on this because we did a lot of the background work talking about caches in the previous video. So if you want a starting refresher on how to do cache problems, I'd recommend looking at the first video. So let's just dive in. So as usual, we're given a set of parameters in our problem that we start with. So let's write them down. Cache size. Here we have a much bigger cache. It's 256 KB. So again, we want to write this as powers of 2. So this is equal to 256 is 2 to the 8, and then the KB part is 2 to the 10. So this is 2 to the 18 bytes. Okay, and then it is four-way set associative with an LRU replacement policy. And remember, LRU means when you're trying to kick out a block from one of the index rows, you kick out the one that was accessed furthest in the past, as in least recently used. So that's the replacement policy there is LRU. And then our block size is 16 byte. So that's 2 to the 4 bytes. And we have the same replacement policy, or the same write policy, write allocate, write back. So again, just to review, that means that whenever you do a write, that means you pull the data from memory into the cache and then write it in the cache. And then whenever you evict the cache line, you write it back to memory. So that's our write policy. Okay, so let's get started. Again, same starting procedure. We want to look at our data and figure out what are the sizes we're dealing with. So first we start out with an integer array. So now things are a little bit different. 1024. Okay. So again, always best to convert stuff to powers of 2. So int, what is that, 4 bytes? So that's 2 to the 2. And how about how many are there? So that's 2 to the 9 is the 512, by 2 to the 10 is 1024. So that's 2 to the 19 integers, which means 2 to the 21 bytes is the total size of this array, because we're multiplying the 19, we're adding the 19 to the 2 here to get the total number of bytes. That's like way bigger than what we've been dealing with in the last problem, but we'll see how we manage that with the rest of our loop. And then, before we continue with the loop, we want to do the tag indexed offset breakdown of our cache. Start with the offset. Well, we have 16-byte blocks for 2 to the 4 bytes, so that's just a 4-bit offset. How about our index? Well, now we're slightly different because we have a set associative cache, which means that every row of our cache now has 4 blocks. So how do we compute that? It's technically the same formula as cache size, 2 to the 18, divide that by your block size, and then divide that by the number of blocks per row, which here is 2 to the 2. And so here we end up with 2 to the 12, which means 12 offset bits. And then our tag, again, unspecified address width, but essentially it's just the remaining bits. So maybe to make this a bit clearer, because this will come into play with this problem, I'm going to write down this is bits 0 through 3 in our address. This is bits 4 through 15 in our address. Yeah. And this is bits 16 to whatever, doesn't really matter, in our address. So these are the bit ranges that each part of our address occupies. Okay, so I think now we can start looking at this loop. First let's draw the cache. Let's visualize this cache. Okay, so we have our 4-way set associative cache with our blocks. So as always, you got a table, and here I'm just going to list blocks, and there are 4 blocks per row. And then there are how many rows? Well, there's 2 to the 12, there's 12 index bits, simply means the last row is going to be 2 to the 12 minus 1 is the last index of our cache. It goes 1, 2, all the way up to this, right? And each one can store 4 blocks. This is what our cache is going to look like. Great. So now we can start doing our parts. So let's write down our for loop. Okay, so the first for loop in part 1. For I equals 0, I is less than 512 times 1024. So we're going all the way through the entire array. And now we are incrementing by 32 times 1024. Now what? This is a very, very large number, so let's figure out, and again, we're just storing a 1, just like in the past problem. So let's figure out this 32 by 1024. How big is this number? How is this going to fit with our cache requirements? So this number is 2 to the 5 for the 32 times 2 to the 10 for the 1024, 2 to the 15. But this isn't 2 to the 15 bytes. This is 2 to the 15 ints, which means since each int is 2 to the 2, that's 2 to the 17 ints, or bytes, I mean. So before we delve into the addresses, let's just look at this. So we have 2 to the 17 bytes. That means we're incrementing I by 2 to the 7, or we're incrementing our address by 2 to the 17 for each new iteration of the loop. Well, let's look at our cache. Let's write down some example addresses before we fill in our cache. So we're going to start with I equals 0. Then I equals 2 to the 15 because I is going to be in terms of integers. I equals 2 to the 16 because 2 to the 15 plus 2 to the 15, right? I equals 2 to the 16 plus 2 to the 15. I equals 2 to the 17. All the way down, what's the last one going to be? Well, this 512 times 1024 is 2 to the 19, so it's just going to be I equals 2 to the 19 minus 2 to the 15, which is our last I. Okay, so let's just break these down before we fill in our cache. What are these going to be tag index offset wise? So offset 0. What's our index? Well, it's bits 4 through 15, so this is 0, and then tag is 0. How about this? 2 to the 15. Well, the first 3 bits are still a 0. How about the index? Does this 15 fall into our index? Well, remember, this is actually 2 to the 17 bytes. So we're incrementing, every time we go forward, we increment the address, we increment by 2 to the 17. So this index goes all the way up to the 15th bit, which means you have 2 to the 17 will increment into the tag. So our index is actually still going to be 0 because these bits are never going to be touched in our stride here. And our tag doesn't particularly matter, but it's going to be 2 bits into the tag, so that means our tag is going to be a 4. And then this is going to be the same story. Index 0 and tag, we're incrementing it again, and so that's going to give us a tag of 8. Yeah. And then same story all the way down, offset 0, index 0, tag, whatever, right? So we can kind of see that this might not be the best scenario for our cache. Let's see how this plays out in when we execute. So start with I equals 0. Well, nothing's in our cache right now, so we go here, write 0 here, and then that's going to be a miss. And what kind of miss? Well, we've never asked for address 0. This is compulsory. How about 2 to the 15? Well, same index, different tag, so we need to put it in a different block. How about this one? Same index, different tag, so we need to put it in a different block. And then this one again, we're going to have to put in a different block, right? So these are all compulsory misses. Okay, and now let's just let's see what happens with 2 to the 17. Well, our offset's 0, our index is 0, tag 16. Well, we go in to index 0, all 4 of our blocks are filled up, and our replacement policy is LRU, which means we're going to fill in the one that was accessed furthest in the past, which is 0. So we're kicking out this block 0, we're evicting it, and we're writing back to memory because it's dirty, and then we're saying, okay, this is going to be where 2 to the 17 is. And again, this is compulsory because we've never asked for this before. And, well, we're going to go all the way down. But before we fill this in, let's just calculate real quick how many accesses are actually happening here. So we have, well, we're striding by 2 to the 15 ints, and there's a total of 2 to the 19 ints. So that's 2 to the 19 divided by 2 to the 15 is 2 to the 4. So that's 16 accesses. And seems like all of them are in the first index, which means we'll essentially fill in this first index 4 times over, because every group of 4 iterations fills in the whole block over. So that means we can kind of figure out what the state of our cache is going to be like at the end of this problem, and it's simply going to be, I'll draw it right here. Well, no, I'll leave it up here. Simply going to be, let's erase this, not enough space. Well, you have the last 4 blocks here, so that's, for brevity, I'll just write 2 to the 19 minus 4, 2 to the 15, 19 minus 3, 2, and then 2 to the 19 minus 2 to the 15. So at the end of the day, all of these blocks, all of these indices at the end are going to be totally blank. We've never looked at them, and the first one is going to be filled in with the last 4 blocks. And all of them are compulsory misses. So for part 1, we have 0% hit rate, all compulsory misses. Okay, so that's done. Let's move on to problem part 2. So here we have a slightly different, I'll just rewrite the for loop. So we have the same limit, we have the same stride amount. The only thing we're doing differently is what we do inside the loop. So this is different. This is plus equals as opposed to just equals. So what does this mean? This means that AI, we read the value and then we increment it by 1. This is 1 read plus 1 write. So for every for every loop iteration, we do 1 read and 1 write. And let's see how this affects our cache hit rate and miss rate. So, well, I'm just going to use the same cache here for the same problem. And for our 16 accesses, let's look at I equals 0. So the same breakdown, but we go back and we have these latter 4 blocks here, so we need to kick something out. Least recently used would tell us to kick out this very first block. So we kick this out. It's going to be a 0. And then we, so that's when the read, so we read it and we kick it out and get a 0, and then that's going to be a miss. And then we get a hit for the write because we're writing the same address, which is already in the cache. Now, let's figure out what type of a miss is this. So it's not a compulsory miss because we've already asked for address 0 before. So let's figure out, is it a conflict miss or not? Well, let's look at our first loop iteration. We're accessing 16 different blocks total. So the real question is, if we had a fully associative cache, could we fit 16 blocks in our cache? Well, our index, let's figure out how many total blocks there are. So there's 2 to the 18 divided by 2 to the 4 equals 2 to the 14 total blocks. So you can fit, what is this? This is 16 KB total blocks inside of our cache, which is way more than 16. So if we had a fully associative cache, we would have only filled in 16 blocks out of 2 to the 14. And so we would have plenty of space and to keep all of the elements, and we would have had a hit here. So this is going to be a conflict miss. How about the next one? Well, it's going to be back to the same plot, back to the same index, and we have to kick out the next one because, again, least recently used. And we get the same scenario, conflict miss, and then we get a hit because we're doing the right. And this is going to happen again for all of our array accesses. We're going to get a conflict miss because we won't have the block anymore, even though we could have had it with a fully associative cache. And we're going to get a hit because we're doing a write. Okay, so what does that translate to in terms of hit rates? Well, for every single iteration we get one miss and then one hit. So that's a 50% hit rate for part 2. And then we get all conflict misses. Okay, great. So that's all there is to part 2. How about part 3? So we have our for loop again. And again, we have the same exact iteration setup. We're starting by the same amount. And now the only thing is different. We're changing again. We're changing what we do on the inside of this loop. So now you have some funky little index here. 512 by 1024 minus I minus 1. And then we're doing the same plus equals. So that's one read and one write. So before we access, sorry, this is a bit confusing, but this loop corresponds to these accesses. Let's think about what index these are going to be. So rather than writing out, since we were going by island, rather than writing out the I value, I'm going to write out what are the indices that we're accessing. So first we got I equals 2, so this is again the end of the array, 2 to the 19 minus 0 minus 1. What's it going to be after that? 2 to the 19 minus I is 2 to the 15 minus 1 equals 2 to the 19 minus 2 to the 16 minus 1. All the way down to the very first block, which is I equals 2 to the, well, I guess it'd be 2 to the 19 minus 2 to the 19 minus 2 to the 15 minus 1, right? So 2 to the 15 minus 1, right? That's the last thing we're accessing. Now, this is different because we're going backwards in the array. So this actually helps us out because at the end of our part 2, the last thing we had filled in, I'm going to go back here because we go through the whole array again. We're going backwards, so we have the stuff from part 2 is going to come into play here. It's going to come in handy. So let's go through some iterations and see what happens. So remember, there's 16 total accesses here. How about access 1? Well, we're accessing 2 to the 19 minus 0 minus 1. So actually, that's going to end up in this very last block over here, because this is all the bytes from 2 to the 19 minus 2 to the 15, all the way up to this very last one. So this is the last byte in this last block. And remember, we're doing a read and a write. So that's hit and another hit. How about for this one? We're just going back a block because we're going back 2 to the 15, and we got the last byte in this block. So we got 2 hits. We got 2 hits for this, and then we got 2 hits for this in our next loop iteration. 3 times 2 to the 15 minus 1, and that's going to be 2 hits. And then what about the remainder? Well, the rest of the blocks, remember, they're not in the cache anymore. So for the first 4 is hit, hit, and then the last 12 accesses, because total of 16, we're going to have to pull our data back into the cache. So for each iteration here, we get a miss for the read and a hit for the write. Okay. So now we are in good shape for figuring this out. How about what type of miss is this going to be? Same story. If we had a fully associative cache, we could have fit all of the blocks, and none of these would be misses. So these are conflict misses. Okay, so now we're in good shape, because to calculate our new hit rate, we literally just tally up all of our hits and divide by the total number of accesses. So hit rate equals, so there's 4, for the first 4, we have 4 hits and 4 hits for the read and the write. And then we have, for the remaining 12, we only have 1 hit per iteration. So that's 12 hits. How many total accesses? Well, there's 2 accesses per iteration for a total of 16 iterations is 32, which means our hit rate is 20 out of 32. And then you get all conflict misses again. And so I guess we did this a little bit differently than usual because usually we'll find a pattern for some local group, but here we had 2 separate patterns, so we just sort of combined the 2 patterns and divided by the total number of misses, or total number of accesses. And then again, all conflict. So that's part 3, and that would be all of the parts for this problem. So kind of to summarize, we had a different setup than number 1 because we had a set associative cache, but we were able to exploit the same type of patterns that we saw in the previous problem, which is going to be the case really for most of these cache problems. You'll find a pattern and you'll be able to generalize across the whole loop without doing the whole problem or doing every loop iteration. So we're able to find patterns for each type of loop and calculate a hit rate and figure out the misses. And turned out for the last part there were sort of 2 separate patterns that we needed to take into account. But we ended up getting the answer using similar methods to the last part as well. So that's all there is to the cache problems in the review. I would look at a lot of cache problems really if I was studying for this test. You can kind of see the flavor of cache problems can change. The way you do them can be different based on the cache parameters, and we can really throw any kind of cache parameters at you. And so doing a bunch of these and just getting sort of in the rhythm of doing these tag index offset breakdowns, this cache visualization, and all of these steps is really good, really important for doing these problems quickly and accurately on a test.